Hi guys, in my last video I talked about introduction to machine learning. So today I'm going to introduce you the first algorithm, how to implement a linear regression model. So in my coming series you need to learn the different kinds of algorithms and how to implement them. So today linear regression. So as I have explained you what is regression analysis. So regression analysis means finding the relationship between the variables, right? And I have also introduced you what are the terms used in machine learning. And here um, the terms like for example this y is equals to ax plus b. This y is called as dependent variable which depends on x, and a and b are some constants. So later on I'll introduce you the terminology in detail. So basically linear regression means finding the linear relationship between the target variable with one or more set of predictors. The predictors are also known as independent variables. So we can classify linear regression into two types: simple linear regression and multiple linear regression. In simple linear regression, so there is one predictor or one independent variable, which is x here. So x is called as predictor or um, independent variable, and y is called as target variable or dependent variable, because y depends on x. Okay, so the main idea between this linear regression and logistic regression is the number of predictors you have towards the right side. So in simple linear regression, only one dependent variable and one independent variables. When you present this, or when you go for visualization, so you'll be having a linear line. You'll be having a straight line which shows the relationship between the y and x. And in multilinear regression, you will be having multiple independent variables. I mean, multiple predictors, we can say, more than one predictors. Here I'm going to take one example, sales prediction, and here there is a data set, and we would like to predict sales based on the money spent on different platforms for marketing. Okay, so decision making. So which kind of advertisement giving you the better sales? So for this, you can go to the Jupyter notebook. So here I'm now implementing the linear regression models. So simple linear regression and multiple linear regressions both. So here is my Jupyter notebook. Um, I think you guys know how to open the new Jupyter notebook. So you must be installed Anaconda, and the prerequisite to my course is Anaconda must be installed, and you must be having the strong basics of Python. So at first, what I'm going to do is this one. So linear regression is used for finding the relationship between the target variable and one or more predictors. If you have one predictor, then we'll say simple linear regression, and if you have multiple predictors, then we say multiple linear regressions. So this is an equation. So y is equals to beta 0 plus beta 1 multiplied by x plus some epsilon. So y is called as dependent variable, or in other terms we say a response variable or target variable, and x is independent variable or predictor. Then what are these beta 0, beta 1, and also epsilon? So here if you look at this figure, this one, so we are finding the relationship between y and x. So y depending on x. Then what is beta 0 here? Beta 0 is intercept. Okay, beta 0 is intercept, and beta 1 is called as coefficient of x. So beta 0 means the distance between the this regression line. This is called as regression line to the x-axis. So the distance, this one, is called as beta 0 intercept. Then what is beta 1? So beta 1 is coefficient of x. So which we calculate as delta y by delta x, mean change in x divided by change in x. So simply we say coefficient of x. So this is what happens in simple linear regression. You are having a line, and this line is called as regression line, As you can see, most of the data is not fitted on the line, so we consider that as error. Okay, outliers, errors of the model. And if the more data is fitted on the line, then that model is considered as the best, right? So this is an equation: y is equals to beta 0 plus beta 1 multiplied by x plus epsilon. What is epsilon? Means some small or error. Okay, and here I will get this residuals, means nothing but error. So what is the model predicting and what is the actual value? If there is a difference between the actual and what the model has predicted, that is called as error, right? So here, so the relationship between the x and y is plotted. So if we know x, here, then this beta 0, beta 1 and epsilon, so they are calculated automatically. And then if we give the input for x, then we'll be getting the value for y. So let us see how to implement a model here. The problem statement over here is we have to build a linear regression model which will predict sales based on the money spent on different platforms for marketing. So as usual, we import the libraries at the beginning, importing pandas as PD. So you guys might be knowing pandas are used to create a data frame. So when you have a data in some files like CSV, Excel, or in some other file formats, you can load the data from the file and then data frame is created. So once the data frame is created, then you can perform various kinds of operations. Then what is the data frame? Data frame is nothing but is a two-dimensional data representation. You'll be having rows and columns. And pandas use a data frame, and these data frames are heterogeneous, means you can have different types of data. So here I'm importing pandas and importing numpy, and numpy is to create a array, as you know, and we need to evaluate model, so that's why importing metrics from scikit-learn, and we have to split the data into train, test, split. So that's why we are importing this train, test, split from the module scikit-learn.model selection. And I kept my dataset in my subfolder data. So pd.read CSV, we are reading the CSV file. What does CSV stands? Comma separated value. And this file is already having the index column like 0, 1, 2. So that's why index column is equals to 0. And we are setting that to 0th column. Then data.head. So if you run this, data frame is created in the cell number 2, and head means by default it displays first 5 rows, and here we have first 5 rows. As you look at the data, so our target variable is this sales. You have to make a decision for sales based on the money spent in TV advertisement, radio and newspaper. Then data.shape. Shape means number of rows and number of columns. So here we have 200 rows and 4 columns are there. So this is clean data. We don't need to do any data pre-processing over here. So that's why we can directly go for data separation next and then building a model. So normally when you have a data set, what we do is we just now split data into train and test. So here when you have a data set like let's say you have a data like this, so this is our target variable. We'll store that into y, and this is your x. X is nothing but set of predictors. You put all the variables or features into x, and you have to separate this into 4 parts. This part is called as train. Okay, this part is called as train, and this part is called as test. This part is called as y train. Okay, y train, and this part is called as y test. Okay, y test. And we can split the data into parts, like 80% is training and 20% is testing. Okay, 20% is testing. There is no fixed rule that you should split into 80-20 or 40-60 or 70-30 or 90-10. Okay, as per the studies, more data fitted, more learning. So there is no fixed rules. As you know, machine learning is just no trial and error approach. You can take some values, and if you are not satisfied with that, it means that if your model performance is not uh, good accurate, then you can change these values. You can later on you can make it 70-30 or 90-10 or 60-40. So we are splitting the available data into two parts. Train, this one is train, this part is called as train, this part is called as test. So 80% train, 20% test. Okay, 80% train and 20% test. So here, as you know, this is a simple linear regression. Okay, as it's a simple regression, so at first I'm going to take the first column, that is a TV. I'm going to take only TV. So investment in TV, then what would be the sales? Means sales value is dependent on TV. So X is equals to data. What is data? Data is a data frame. You are getting only TV. And in Y you are putting sales. And then this train test splitting X and Y into four parts: X train, X test, Y train, Y test. And the test size is 0.2, 20%. Random state you mentioned 0 here. Random state 0 means the rows are accessed in sequence. If you give some random value, so that means reproducibility, and the model will be getting your random rows. And then so we are importing the algorithm. Import linear regression. This is our algorithm from scikit-learn.linear model. And then creating object to the class. So basically this is a class, so creating object means model is created over here. And then you need to fit the values. So fitting data to the algorithm or model is nothing but model is learning. So here the model learn, and then as I mentioned before, this beta 0, beta 1 are calculated automatically. So we would like to display the intercept values. This is predefined constant, intercept underscore, and this is coefficient, means beta 1. So when you run this, the model is created. As you know, beta 0 is 7.29, this is beta 1, and if you give input for TV, then you will be getting the value for sales. So here you can see we are using our model. So SLM is the model name. So SLM dot predict, making the prediction for sales. And what is the input here? 100, means TV value is 100. For example, if you spend $100 in TV advertisement, then what the model is predicting? So the model has predicted that 11.89 is the sales value. Okay, 8.89 is the 11.89 is the sales value. So we have 20% data, so making prediction for complete 20% data. So the predictions are these. Okay, predictions are these. So before I go for no building another model, so now let us take, instead of TV, I would like to take a newspaper, let's say. Means if I invest $100 in newspaper, if I invest $100 in the same newspaper, then what the model will predict. So we got 18.43. So this is better than the TV advertisement. With TV we got 11.89, but with newspaper we got $18.43 as the sales value. Now this time I would like to take a radio. For radio advertisement, okay, for radio advertisement, what is the sales value? So running the model again, then making the prediction. So this time you got 30.03, $30.03. for sales. If you invest $100 in radio, so with this analysis, so we can understand that radio advertisement is better to get better sales. This is as per data. Okay, this is as per data. Radio advertisement is better. Next, making the prediction for this, and then so every model has to be evaluated. So we are calculating this mean absolute error. We are not doing this manually. We have predefined methods like matrix dot mean absolute error. Error means, as I explained you, the difference between y test. What is y test? This is actual value, and y predict means what the model has predicted. So you have the predicted value here. So if there is a difference, then we call it as error. So mean absolute error, and you are also getting mean squared error between y test and y predict, and you are also printing root mean square error. So there is no direct function for root mean square error, so that's why after calculating mean square error, we are applying square. Then so you can see these are the values. Mean absolute error 3.71, mean square error is 24.23, and root mean square error value is 4.92. Okay, so there's no need to consider all. So even if you consider one of the metric, then that's enough. So most of the time we'll use this RMSE, root mean square error. So this much is the error for this linear regression model. So if we go into details how these errors are calculated, so we can check that over here. So these are the equations. So mean absolute error means, so the difference between actual and what the model predicted, and all these values are summed and then divided by n, and you have mod between this. So mod of actual minus predicted, summing up all these values and then dividing by n, so that gives the MAE. Mean square, square means square root between the yi minus xi square, then dividing by summing and then dividing by n. Then root mean square, root mean square is nothing but square root of MSE, mean square error. So you can consider one of the metric to evaluate your model. So here let us say this 4.92 is the root mean square error for the linear regression model. So next let us build another model, that is multiple linear regression. So what is multiple linear regression? You can take more than one variable. Okay, more than one variables. In other terms, we can say multiple predictors or multiple independent variables. So I'm taking a list here. So this is Python list. So feature column is equals to TV, radio, newspaper. So if you invest all together in these TV, radio, and newspaper, then what would be the sales? So X is equals to data of feature columns, means all the rows are accessed into X, and then in Y we are putting sales. Then again splitting data into 80%, 20% here. Then the data is splitted. Importing the algorithm, no need to import multiple times. So if you import only once in the current notebook, then that's enough. Importing linear regression from scikit-learn.linear model, creating object. Okay, creating object here. So this is the model name, multiple linear regression is equals to linear regression, and we are fitting data to the model, then model learn, and printing intercept means beta 0, and coefficient. So here we have multiple coefficient, means coefficient of TV, coefficient of radio, coefficient of newspaper. And here we can write up the equation again, like we can write like sales. Okay, sales is equals to, you can write sales, sorry, sales is equals to, okay, sales is equals to beta 0, okay, beta 0 plus beta 1, so beta 1 into TV, okay, beta 1 TV, plus we can write beta 2, so beta 2 next coefficient is this one, radio, plus beta 3, okay, beta 3 into newspaper. So as you know, this beta 0 over here is written by this. Beta 1 is also returned, beta 2 is also written, beta 3 is also written, and you know the value for TV, radio and newspaper. So if you substitute all these, then you'll be getting the value for sales. Okay, you'll be getting the value for sales. So this is your beta 0, this is beta 1, this is beta 2, beta 3. So you know all these, and if you give the value for TV, radio, newspaper, then you are getting the value for sales. So here using our model MLM and making the predict of TV value I'm giving 100, radio 100, newspaper 100. So if you spend $100 in each medium, then totally we are getting 26.82 sales value. So we are almost investing $300 over here. With the $300, 26.82. Then making the prediction for complete 20% X test. So these are the predicted values, right? And we can also evaluate the model. So if you evaluate the model, like what is the mean absolute error, what is mean square error, and what is the root mean square error, so you will be getting the value. So root mean square value is decreased here, 2.09. So this model is better. Okay, this model is better in terms of error, 2.09, but the sales value is not that much accurate, right? So with the multiple linear regression model, we got RMSE value is 4.92, and here depends on the value you take, radio or newspaper or TV, and here also you are getting the 2.09. So before you evaluate a model, and you can also find the relationship between the variables like TV and sales. So we can, by using Seaborn, you can plot regression plot. So here we are importing Seaborn as SNS, then SNS dot regression plot between this TV and radio. So you can see there's a positive relation. Means if the TV value increases, then the sale value also increases. So there is a positive correlation. And also you can see majority of the data is not fitted on the regression line. So that's why we got the error. Similarly, you can check the relationship between radio and sales. So how sales value depends on radio. So here we took TV and here we are taking radio. So there is also positive relation. Now let's see the relationship between newspaper and sales. So here also positive relation, but not that much high. Okay. So this is how you can build a linear regression model for the given data set. I hope I tried to explain you how to build a simple linear regression model and multiple linear regression model. So next I would like to take one more example in building the regression model. So here we have a data set, and with this data set we would like to make the prediction. So score student, so predicting the percentage of marks the student is expected to score based on the number of hours studied. Okay, so here I'm importing pandas to create a data frame, importing numpy to create a numpy array, importing seaborn for data visualization, importing matplotlib, right, importing matplotlib for data visualization, and sometimes we get some unnecessary warnings, so we would like to hide them. So once the libraries are imported, you can go for importing your data. So this is the file studentscores.csv I kept in my data folder. So data slash the file name, this CSV file is read and the data frame is created. The data frame name is data here, then data dot head. So these are the first 5 rows. number of hours and score. So we will take a square as a target variable and hours as a independent variable. So if the number of hours are increased, then score is going to be increased or not. So obviously score increase, because if you increase more hours, then score increase. So you can also plot the relationship between these two variables, hours and score. So by using matplotlib, on x-axis I'm showing hours and y-axis showing scores, and specifying the font size as well, 15, and here also 15, and hours studied versus score. So we are this is going to be a title of the figure, then font size mentioned as 10, and we are plotting a scatter plot here showing the relationship between the hours and score. The color used is blue and the marker is star. So this shows the relationship between the hours and score. You see the relationship. So there is a positive relation. Okay, there is a positive relation between the number of hours studied and the final score. And you can also find correlation. You can also find the correlation between the two variables. So specifying the figure size here, plt dot figure size 4 by 4 means 400 pixels width, 400 pixels height, and we are finding correlation. This is predefined method CORR, correlation. It will find the correlation and will have a matrix. This is user defined variable, and also we are plotting a heat map here, SNS cbond dot heat map. So data is correlation matrix, annotation is true, then plt dot show. So we just have two variables here, hours and score. You can see the hours score relations, correlation 0.98. Okay, 0.98. So this is a heat map, right? So it depends on the color scale here. You can see the color, and you can also manually display what are the values. So hours is always 100%, even score is always 100%. Hours score 97.6191, here also the same score and hours. Now this is also clean data, so I'm just putting all rows here. I location means locating the rows, data dot I locate all rows. Then how about the column? This is slicing, so getting the first row. So first column is put into X and the second column is put into the Y. So Y is equals to, this is negative indexing. Okay, so 1 means score is put into Y. Then as usual we are now splitting data into 80%, 20%. Test size is 0.2 means 20%. Random state also here 0, and we are splitting X and Y into 4 parts: X train, X test, Y train, Y test. Then the data is splitted, and then importing the algorithm here, linear regression from scikit-learn.linear model, creating object to the model, linear regression, fitting data. The model always learns from trained data. This is the point to be noted. So model always learns from trained data, not test data. And then we'll display this message, training complete. Then we are also getting the intercept and coefficient values into B0, beta 0, beta 1. These are the user defined names. So beta 0 is this much, this is beta 1, and we are calculating manually here. So y equals to linear regression dot beta 0, this is coefficient multiplied by X train. Then we are also plotting this using a scatter plot, X train, Y train, color is green, marker is plus, and also plotting X train, and these are the x-axis label. X-axis label is hours, y-axis label is scores, specifying the font size for both. This is the title, font size for title is 10, showing the graph. So you can see these are the points. So there are less values fitted on the regression line. Then making the prediction. So displaying the X test, we have 20% our values, and then using our model. This is the model name dot predict. making the prediction for X test. These are the predicted values: 1.5, 3.2, 7.4, like this. So this is the prediction for X test. Then also creating a data frame to see what is the actual and what the model has predicted. And you can see here the actual is 20, the predicted value is 16.88. okay, the score, this actually 27, this is 33.73. so actual versus what the model has predicted. These values are some values are higher, some values are lower, but a model is going to be having a similarity based on the data fitted. Now also plotting the graph here. So df dot plot, we are plotting a bar chart. Figure size is this, color is blue, green, this is the title. So actual versus model has, there is no much difference between actual and predicted. Actual is represented by blue color, model predicted is green color. Now we have to evaluate our model. So these are the metrics: mean square error. So I have explained you how to calculate this. And R square is also metric. So R square tells us how much data is fitted. And mean absolute error, MEAE. So displaying these MEAE. So we no need to do any manual calculation because we have predefined methods. So mean absolute error between actual, what the model predicted, then printing. Then again square root of MSE is RMSE. And for R2 also, R square also, we have the predefined method which we have imported, then displaying the value of that. So RMSE value is 2.04 and R square value is 0.94. 94% of the data is fitted. So you can see that here the performance is 94.55 accurate. This much data is fitted, and the uh, RMSE value is 2.04. Like this. Also, if you give some input, now we have built a model and the model has been trained. Now we want to take input from the user. So user input equals to, we can use Python's input function, converting that into float because the actual values are float here. The number of hours are float. Then it will give you the score. So converting the input into float, then formatting in user input, and also using our model linear regression dot predicting for the user value. Then it shows us what is the value. For example, 2.5 hours studied. Then what is the score? The score is 26.79. And finally, you can also save your model. So importing pickle by using the pickle library, this file is going to be created. And this is the mode of the file, write and binary. Then dumping the value of model, you can finally the file is closed. So guys, like this, when you are given with some data set, you can build a linear regression model. So there are two types: simple linear regression and multiple linear regression. And we have taken two data sets here. In the first one, we have built simple and multiple. In the second data set, with the second data set, we have built only simple linear regression model because there are only one independent variable and this is dependent variable. So that's it from me today. So if you have any questions, feel free to reach out to us, and do subscribe so that you can get our classes, regular sessions updated to you.